Ladies and gentlemen, hello and welcome back once again to the briefing room. My name is Eric Cavanaugh. I will be your host for today's event, which is going to cover a very, very exciting topic today, folks. We're going to be talking about a technology that is truly disruptive. It's been around for a long time, but for a variety of reasons, it's starting to get into a position where it's going to significantly change how big parts of this industry are executed, about how big things are done in the world of information management, business intelligence, analytics, so on and so forth. The topic for today is in-memory. So we're going to talk about how in-memory computing is going to change the fundamental way in which business is done here in the field of information management. So there is a slide about yours truly and enough about me. As many of you know, the mission of the briefing room is to reveal the essential characteristics of enterprise software. So what we've done is we've taken a different approach in performing webcasts, in putting on webcasts, where we actually expose a live analyst briefing. So unlike most of the other events you'll see, where the analyst goes first and then the vendor goes second and says, I'm so glad you made all those statements because we have a perfect solution for it. Instead, we turn that around. So we have the vendor go first for 20 minutes. The analyst then gives a brief response. They get a week to review the slides of the vendor, and then they just start asking questions. So it is a live analyst briefing that we're going to be experiencing here today, as every Tuesday at 4 Eastern. So we cover a different topic every month, and the reason there is because we're trying to give all of you as good a comparison of technologies as we possibly can. Obviously, if you are in the position to purchase enterprise technology, you know that this stuff tends to be fairly expensive, which means if you're going to do it, you want to make sure you do it right. And so that's why we have a different topic every month, because we're trying to give you, as the audience out there, some apples-to-apples comparisons in domains such as analytics or integration or database or cloud. Once in a while, we do a bit of a curveball. So July is disruption. And the reason is because we looked around and saw that there are so many interesting things happening that really will fundamentally change the way business is done. So if you logged into the event early, you probably heard me chatting with our guests about the power of Twitter. So Twitter is just one disruptive force out there in the market these days. Of course, it's a social media style of disruption. Facebook, of course, just had their IPO, which didn't go so well, but still, nonetheless, Facebook is a huge force to be reckoned with out there in the world of technology. LinkedIn, Twitter, a whole variety of other social platforms are changing the way business is done. Well, there's another force that's changing the way things are done, and that is the power of in-memory, or the power of RAM. So the analyst today is going to be Robin Bloor, and he just posted an article yesterday on our website, InsideAnalysis.com, where he talks about how in-memory changes the way things are done in the world of computing. If you think about the fact that depending upon the test case, accessing RAM can be up to 100,000 times faster than accessing disk, 100,000 times? That's not a small thing. And so because memory is getting cheaper and cheaper by the day, think about what that does for the way that you architect solutions. Your entire information architecture can change now, and I would encourage you all to consider just how big a deal this is. So the company we're going to be talking to today is GridGain, a Java-based open source middleware for real-time big data processing. So we're going to be hearing from Nikita Ivanov. You can see his bio right there. He's been in the business for quite a few years now, 20 years in fact, in software application development. He's a pretty smart guy, and I'm going to go ahead and hand the keys to the WebEx over to him right now. And yes, folks, I will post a link to the slides for today in just about 1 minute. So with that, Nikita, I have given you control. Go ahead and click anywhere on that slide and use the down arrow on your keyboard to move forward.
Excellent, Eric. Thank you very much for the introduction, and I want to welcome everybody in this webcast. My name is Nikita Ivanov. I'm the founder and CEO of GridGain Systems. So I want to basically start off, we're going to talk about GridGain and how GridGain solves some of these problems with memory processing. But I really want to start off with basically spend a couple of minutes discussing why we're talking about big data and what is in memory, some of the general facts about in-memory processing, while all of a sudden we talk about this subject. So we start with the big data, and it's an interesting phenomena because, most of the IT businesses, most of the businesses that have any IT were dealing with the data processing and data collection for decades. Essentially, from day one, we had these computers in the businesses. So what happened that all of a sudden in the last couple of years that became such a huge phenomenon and everybody talks about big data? Well, in my opinion, there are several trends that actually collided at a certain point. One of them is the dramatic reduction of a cost for a disk-based storage. I recently spoken to another group, and it came out very interesting, kind of residual that a disk-based storage today is essentially free. The terabytes kind of a size consumer electronic devices cost just a few $100s. And for a corporate environment, such cost is essentially free. People talk today more about a power consumption, heat consumption, rather than a cost of actual disk drive. That's a dramatic change from 10, 15, 20 years ago where disk storage was fairly expensive. So today, essentially, the capacity problem is solved. Yet another trend that actually rather dramatically increased over the last several years, maybe half a decade, is the data growth. Essentially, we are capturing dramatically, exponentially more data with every year passing by. Look at this chart, the illustration on top of the slide. I think it's a very good illustration. 10 years ago, for example, if you have an online store, you were capturing just a purchase transaction. That was a typical recording point. You were recording a transaction, a purchase, or a trade made, or something like that. Today, we are recording all the different events that actually are in between those transactions. If you take an example of online store and a purchase, and let's say two purchases, there are so many events for a single user between those purchases. You can go on a certain page, click on the link, post on Facebook, post on Twitter, and plenty of other activities. And many users self-documenting their behavior online. So that's the essence of the big data explosion, that all of a sudden we're not only recording a singular events, transactional events, we're recording all the other events that happen in between, and we have a dramatic growth in those events. Look at the population of Facebook ecosystem and Twitter ecosystem and everybody else. That is the essence of why all of a sudden the big data processing is becoming such a big concern. So from a definition standpoint, I think most of you heard that we're talking about often about the 3 V's of big data: volume, velocity, and variety. In my opinion, the volume is self-explanatory. You have to have a certain amount of data to be quote-unquote qualified as a big data. If everything fits in your laptop, it usually is not a big data. But if you need a fairly significant amount of storage, usually you have a big data system, a big data issue. Velocity is probably one of the most interesting one because it talks about how frequently data is changing. Because if you think about the edge case where data is completely static and it doesn't change at all, then you have very different ways to process it and a lot more effective ways to process. Unfortunately, in real life, data is changing constantly, and we often talk about streaming data that is constantly coming into businesses, and their velocity is a very important characteristic of a big data systems. Variety, in my opinion, is a kind of oddball. It talks about different types of data, and for me, that's pretty much, what's new? Data is always going to be different. It can be structured, unstructured, and so I don't really put too much weight on this. What actually happening right now is that many people realizing that we're missing something from this picture. And the missing letter, if you will, is speed. Because if you notice in the 3 V's I just described, we never talk about how quickly it can process the data. We talked about the volume, we talked about velocity, essentially how frequently data is changing, but we never talk about how quickly we can process this data. And this concern is becoming, bigger and bigger. And there's a whole term coined around it called fast data, essentially, as a big data system with emphasis on how quickly data can be processed. And it's becoming very, very important. So in-memory is one of those technologies that even Gartner says, for example, that in-memory will have the industry impact comparable to web and cloud. That's from Massimo Pazzini. That's a pretty bold statement. I'm not sure I entirely agree with that because I think it's a little bit overboard. But it tells you how much certain analysts and certain industry groups put weight on in-memory technology because it does have a essentially DNA of have a very profound effect on how do we build systems and how do we process large data sets. Let me just give you some technical facts about a memory that actually sometimes very amazing. 64-bit CPUs, the same CPU you have in most of your laptops today, and in 2 or 3 years you're going to have in your iPad and iPhones, can address up to 16 exabyte of data. It's essentially, it's more than all the data we have today in the world can be addressed by a single CPU. So essentially, we've solved the capacity problem by, of having, addressable space in our computing industry. Another interesting fact is the RAM prices, the memory prices, follow very much the same trend of disk-based prices by dropping out 30% every year and a half. Remember a couple of minutes ago I told you that today, for a corporate environment, the disk space is essentially almost free, if not entirely free in many cases. And the RAM actually goes to the same level. And it may not be free right now, although gigabyte of RAM costs today less than $1. In the years to come, in less than maybe half a decade, the cost of memory will become basically irrelevant. It will become compatible with the heat problems, with power consumption problem, with any other not related to the cost of actual RAM problems. Let me give you an example of how economical the RAM-based storage became lately. We at GridGain just purchased a test cluster, basically for testing our own software. And this cluster has about 12 blades. It's a Dell, middle-of-the-road Dell blades. And the total capacity of this cluster is 1 terabyte of RAM. It has about 50 cores. Total cost to us with delivery, less than $40K. Think about this. For less than $40K, which is like 3 salaries of engineer in Silicon Valley, you can purchase a cluster of, dozen of nodes and have a total capacity of 1 terabyte of RAM. Just to give you a kind of, a reference point, you can keep probably about a week of global tweets in memory if you have 1 terabyte of RAM. Now think about this. For $40K, you can keep all global tweets for entire 7 days, all of them in memory. And once you have it in memory, you can do all type of parallel analysis, and almost everything will happen under a second in real time. That's a very powerful statement because even like 5, maybe let alone 10 years ago, that was unattainable. The RAM prices were dramatically more than that. The overall pricing of the hardware was much more than that. And we were talking about in a 10x price difference than today. And today it's practically available for any type of business. Another interesting aspect of, of a memory facts is that, we now have a lot more cores on a single CPU. And that was actually a very interesting point because, in the last decade and in the 90s, there was a very prohibitive or kind of technical reality that we can have probably, if you can pay enough money, have a lot of memory, but you had only one physical processing core, one CPU. And therefore, you didn't have this inherent parallelism on a hardware level to support all that large memory that you can have. Today, with 8, 16, 24 cores per CPU, or multiple CPUs on a system, we have that parallelism that actually allows us to very effectively process large data sets. Now we talked about some of the facts. Why we're talking about in-memory? Well, it may sound obvious, but actually it's a very interesting slide. The speed matters. And I think we all intuitively understand that speed matters. It's always kind of hard to come up with the fact why it matters. I pulled some of the interesting facts. So Citigroup says that, for example, in the Forex trading, in 1/10 of a second delay on a Forex trade cost him upward to $1 million. Google, for example, claims that half a second delay on the on the search results cost them 20% of the traffic. And if you know anything about Google, traffic means revenue, and 20% of the traffic practically means billions of dollars. So half a second delay on the search query cost them literally billions of dollars in loss. That's why companies like Citi and Google and many, many, many others, invest a lot in performance. And one of the areas of investment is in memory processing. Most of the new Google projects like Percolator and Dremel, they're all based on in-memory technology and moving away from disk-based processing, exactly because of these business drivers. I think Eric said, by the way, that the disk is 100 times slower. I think the proper number, at least the one that I saw, is up to 10 million times slower than the RAM. Obviously, this number should be very clear to say up to 10 million times, but that's a staggering gap in performance if you consider this. And for me, from a software perspective, it's not that. I mean, the gap itself is very revealing, but what it tells me even more is that when you have such a qualitative gap in performance, it enables a completely different level, a completely new family of algorithms that we as a software engineer can employ to process the data in memory. Because again, the gap like that is not only about speed, it's about enabling a very, very different type of processing. Something we do at GridGain, something Google did with their own projects, and that's one of the fundamental reasons why in-memory processing can deliver such a great result in performance and scalability. One of the interesting ways to look at in-memory is what I had on this slide, the in-memory computing tenant. It's kind of historical looking and I think it's very easy to understand. So RAM is a new disk, and a disk is a new tape. If you look back, let's say, late 80s, mid-90s, most of the systems we were building back then, it was a client server and all those different technologies, where essentially data was stored on a disk, on a spinning disk, and the tape was used as a backup, as an overflow, as a generic data warehouse for long-term storage. So today, it's actually changed. It's changing rather quickly. Today, we're trying to keep as much data as in RAM, in memory, and we use disk as a typical overflow storage, as a typical recovery, as a backup, as a data warehouse like Hadoop-based systems to essentially store data for a long term. So that's actually probably a very concise and very quick way to think about in memory. That today RAM is a new disk and the disk is a new tape. So on this slide, I want to talk a little bit about the comparison between disk-based systems such as Hadoop, for example, and memory-based systems, where they're good and how they actually work together. The first important point that neither one of them is exclusive. They all serve slightly different purposes. When we're talking about the disk-based systems, and I could use example, for example, of Hadoop HDFS and the Hadoop ecosystem, we talk predominantly about ETL data. If you have a Hadoop system, you got to have a batch process to load data into Hadoop. You never work with Hadoop directly. You never store your trades or your clicks into Hadoop. You essentially have some kind of OLTP SQL system, and then you have a nightly process that loads data from your Oracle database, for example, into the Hadoop. That's the ETL process. When we're dealing with memory systems, most of the time they're designed, and GridGain is a perfect example of that. They're designed to keep the live data. The difference is very simple. If somebody made a trade, if it's a trading system, this trade will appear in your analytics tomorrow if it's a Hadoop-based system, and this trade will immediately available for your analytics if it's in memory systems. Different types of analytics, different requirements. Sometimes you're okay with the overnight processing. Sometimes you need it right now. This right now is handled by in-memory. Obviously, disk-based systems are operating on disk speed. There's no magic around it. In-memory systems operate in RAM speed. Again, pretty obvious. I think the key point on this slide is really understand the best and most convenient, and not convenient, the most fitting use case for a disk-based systems. And they're excel as a data warehouses. Somewhere you keep data for a long period of time, and essentially you worry about the volume, capacity, and the reliability of the storage for a long, extended period of time. In-memory systems are a lot better at data processing. You don't keep data in memory for years and years. That's just not right medium. But you keep data in memory to have a real-time, low-latency processing, and therefore in-memory systems excel in data processing. So to summarize this picture, essentially, is what I define as fast data as essentially a combination of data warehouses plus in-memory processing. You get the best of two worlds. You get stable, reliable, disk-based years and years of data storage, and you get in-memory processing that can keep a working set in memory and give you this instant, low-latency, real-time processing capability. So what about GridGain? So GridGain is essentially designed to support and solve many of these problems. In short, GridGain is a scalable in-memory data platform. Technologically, we're essentially a combination of two key technologies, in-memory compute grid in-memory data grid. And I will have two more slides about each of them. We support all types of different, all the different types of data processing, whether it's a MapReduce, streaming MapReduce, complex event processing, and traditional RPC and API type of processing, whatever reference you can have. We've been independently tested to support up to terabytes of data in memory and thousands of nodes. So we are a fairly mature project. We started developing our project in 2005. The first version came out in 2007. And so we, as a production software, we've been in the business for more than 5 years. We have a pretty good stable list of clients and large community of users. Our software starts every 10 seconds around the globe, and so we're doing something right about that. If you ask me about what is the kind of quick way to define what are the intricate qualities of GridGain, I would say basically we provide you in-memory speed with database reliability. So we're trying to give you as much as we can the best of two worlds. We're trying to give you a very reliable in-memory data platform with a full transactional support, with a full failover and all of different technologies like that. But we're also giving you this in-memory speed that you can build your system to process large data sets, process large computational loads in actual real time, often in under a second and in milliseconds. Technically, we're Java-based product. We support all the new languages such as Scala and Groovy, for example. From a client connectivity perspective, we support many other languages like C++ and .NET. We're about to announce our mobility strategy with supporting iOS devices like iPhone and iPad. We support Android already. Things like PHP, REST protocols, Memcached, all of this we support right now. So on this slide, I really want to give you a quick glance at where the typical or what the typical architecture with GridGain would be. And obviously, every system would differ and sometimes in very dramatic ways, but often we find that GridGain is used right in the middle between an application and enterprise data stores, whether they're OLTP SQL data store, a combination of OLTP and HDFS, or just directly HDFS like Hadoop data store. GridGain provides this in-memory layer between your applications and your actual data warehouses, if you will. And then essentially your applications, your analytics, your BI, your operational BI systems can talk to GridGain and really enjoy and benefit from that low latency real-time processing capability that GridGain gives you. GridGain has a very unique intelligent technology to cache data properly so that you don't never have inconsistency of your data between the data store and in memory. So essentially you can treat GridGain as your main system of records, and GridGain will intelligently save data into the data warehouse when it needs to be saved. It's a very interesting technology, and it's very simple to deploy in this way because you don't really have to re-architect your system dramatically to put a GridGain in. The last couple of slides I have, I want to give you a little bit of a technical overview about a compute grid in a data grid, and I have a few minutes left. The compute grid, and we have many different names for the same idea. It's a very simple idea. We've had it literally for, I actually recently calculated, we have it literally for about half a century, if not longer. So essentially, if you have a task and you have, let's say, 3 computers in front of you, what you can do to speed up the processing of this task, you can split this task into multiple, let's say, into 3 subtasks, and then you can send each subtask to this individual node. Let those 3 nodes process these subtasks in parallel. Then you get results back from those 3 nodes and aggregate them to get the final result. So in ideal case, if you have 3 nodes, you can process this task in 1/3 of a time. Clearly, because those nodes were processing those subtasks in parallel. That's frankly it. That's all there is to it, to any parallelization, to any compute grid technology. There's obviously plenty more details. How do you fail over? How do you load balance? How do you resolve your collisions? And a myriad of other things that every vendor provides. But fundamentally, the idea is very simple. And GridGain has one of the most, if not the most advanced implementation of this technology. We're undoubtedly #1 HPC platform in the world for Java and JVM ecosystem. We have a very sophisticated support for MapReduce, streaming MapReduce complex event processing with very advanced algorithms for load balancing, the failover, the collision resolution, deployment, and all other different aspects of how do you dealing with the computational loads. Data grids, in-memory data grids in particular, solve a similar problem but slightly different context. If compute grids talk about how do I parallelize processing, data grids talk about how do I parallelize data storage. Think again, it's a very similar problem. Let's say you have a terabyte of data, and you have only computers that can hold up to 20 gigabytes of RAM. How do you put this? So obviously you have to partition this data and put certain chunks of data on one computer, another chunk on another computer, and so on and so forth. So once you do that, you open proverbial can of worms, because that dramatically complicates the way for you as a developer, as an engineer. How do you transact this data? How do you access it? How do you query? How do you store? How do you make sure it's failed over? And all of those different concerns. So all of those different concerns are handled by a data grid that provides you a fairly simple and canonical view on your data, despite the fact no matter how it's partitioned, how it's actually physically stored. So the combination of compute and data grid is what GridGain is all about from a technical perspective. That's the what I would say technological DNA of our product. We're the first product that combined these two technologies into the under one roof. So you get a consistent and single point of documentation, configuration, a canonical API, canonical philosophy behind the product. So you don't have to. So your engineering teams don't have to integrate apples and oranges and try to make them work together. And the last slide I have is essentially just give you a quick look at how GridGain is used. And we have a pretty good list of customers who's using us. And we've been used for a variety of different industries, but I'll give you some of the that actually we consider to be a kind of trademark usage for systems like GridGain specifically, trading systems. We've been used on I would say, pretty long list of customers that use us in trading systems for high, I would say, large volume transactions and real-time processing and trading and trade reconciliations and portfolio management and all those different use cases. Real-time risk analysis, again, similar tasks, analyzing positions, risk during the trading. Online gaming, we have a few titles from Sony, for example, that are public that use GridGain in the back end. And it's very interesting technology because I was surprised myself when I learned about it that many games today have a lot more engineering put on the back end than the front end of the games. And the back end of the games is where the real revolution happens in the massively multiplayer online games. Real-time analytics, very canonical use case for GridGain. Any type of analytics, BI, operational BI, where you have to analyze live data to make the business decisions to change the way you trade, to change the way your inventory works, and plenty of other use cases. GridGain is a perfect example. I think actually Apple is using us for a very similar use case. Geomapping, again, it's a canonical use case for systems like GridGain for in-memory processing because geolocation is inherently a real-time concern. You don't stand in a single spot in GPS, for more than a few seconds. So, to geo-track and do the hyper-local advertisement, you have to process data extremely fast and you have a hardcore SLA. And again, it's finally bioinformatics. It's one of the areas that's been, in the forefront of using anything that can help to process things faster. It's image processing, DNA sequencing, analyzing large data sets, and they always have a time constraint. And GridGain has been successfully used in several use cases like that. And in-memory systems and high-performance systems in general are very much our everyday tool for those guys. So there's my last slide, and I'll be happy to answer any questions.
That sounds good. And with this, I'm going to go ahead and hand the keys of the car over to my partner in crime, the infamous Dr. Robin Bloor. Robin, just click anywhere and use the down arrow on your key. There you go.
Okay, I didn't realize I was infamous. But I'm okay with that. I decided to call this presentation The Persistence of Memory simply because I think memory is going to persist in a very particular way. I think it is actually going to become the prime medium of data, and that absolutely isn't the case right now. So let me just start by giving a perspective that's based upon hierarchical data store. We've lived with hierarchical data store for decades. And basically, you could look at it. I mean, I've drawn a very simplified diagram here, but you can look at it in this way. We have, you know, the most valuable data in sense of closest to the processing sitting in RAM. We now have solid-state disk. That's getting fairly common now in various places, and that's faster than a local disk attachment, a local HDD hard disk drive, and that's faster than SAN. And then we have things, data in archive, which in one way or another is on optical disk or it's on tape, or maybe it's just on disk spinning somewhere slowly somewhere in the organization that don't matter too much. But basically, we can see, looking at the right-hand side of this, we can see that there's a tendency for data to rise up this diagram. And this has been going on for a long time. And we can look at it this way. You can say that there's unstored data we never tried to process in any way. And it gets into the flow of things. And that's what big data is all about. And it kind of moves up the tree. Part of what's happening with data is, with big data, is some data that's archived is no longer archived. It's stuck in the SAN to allow more detailed analysis of it. And then in terms of the value of what you're actually doing with the data, it kind of moves up this hierarchy until it gets into RAM, where it's going to be processed much faster than anything else. And applications kind of span this whole space. And the question that we're asking here is, well, what happens when memory takes over? So the next slide I've got is just really a list of the facts around hierarchical store. Memory access I calculate as 100,000 times faster than local HDD. But it's worth noting that the disparity in speed between these two is increasing in favor of memory, and is likely to continue to increase because the ability for HDD itself to actually speed up seems to be slowing down. Memory costs are declining roughly 30% per annum, according to the set of data I looked at. Memory costs are currently about 500 times HDD cost. Then we've got solid-state disks. It's anywhere between 3 and 5 times faster than HDD, but it actually turns out that it's 3 times faster to read, and if you want 5 times faster, that tends to be writes, which is actually a good thing in some ways. It's 15 to 20 times the cost of HDD, and the cost is declining about 50% per annum, much faster than the cost of memory. Local HDD, 3 times faster than SAN or NAS usually. Cost declines at about 35% per annum roughly. But so does SAN and NAS because it's all the same technology, just bundled up in a different way. Now if we look at a slide of all of those things, what I've done here on the left-hand side is I've actually got a logarithmic scale, otherwise the graphs would blow your mind. So what are exponential declines in cost of memory and SSD and HDD are represented as straight lines, and I'm taking the data growth to be about 55% per annum, which is sometimes above that. In the worst possible year in recent times, it dropped to about 40%, but it seems to go up 55%. So if you look at this picture, you can just see that in one way or another, data keeps on rising, and the amount of data is rising faster than the decline in the price of any of the other stuff. And there's no reason to believe, because these are actually long-term trends, there's no reason to believe that this is going to change much. We might, I would speculate that HDD, I mean, you know, where these cross over in terms of when memory becomes as cheap as disk is now. And that's, you know, at this rate of decline, that's going to be 18 years. That's a long time. But the HDD SD cost is probably going to converge much more swiftly than shown here, simply because there's little possibility of HDD continuing, you know, the technology itself, spinning disk, continuing to be viable over time. And SSD is getting serious economies of scale going for it, which is why it's declining so fast. So they were probably cost earlier than shown here, but I faithfully reproduced this from trends, all of which I think have been established over about 10 years. So, you know, these are not short-term trends, these are long-term trends. But, you know, the main takeaway from this slide is that data is increasing much faster. You know, so if we go back to the last slide, well, sorry, the slide before that, we aren't going to have everything in RAM. We're still going to have this situation where RAM is going to be holding the valuable stuff. And we might see spinning disk disappear. We might even see archive in its current form as state optical disk disappear. But we will end up with disk simply because the data is growing too fast. Unless there's something even more disruptive than what's currently happening with memory, that's gonna occur. So what I wanted to do, I use this graph quite a lot, this kind of illustration. It takes a little bit of talking through, but it's kind of worth it. Again, on the left-hand side, we have a logarithmic scale of response times. And along the bottom, what we have here is a rough estimate of workload sizes. And workloads can be big because there's a lot of data being processed, or they can be big because there's a lot of analytics on, let's say, lesser data. So it's a kind of rough scale. But if you look, what I've drawn here is various curves starting in 1960 and roughly estimating what the actual response times were in those days, and going down through 1970, 1980, 1990, 2000, 2010. And I've drawn these colored bars in just to indicate that, you know, we still have things, we still have what we would call slow batch jobs, we still have things that will take a day to process. Again, we have what I've called medium batch, which is where, you know, the processing still takes, you know, quite a lot of minutes or hours. And we have fast batch, which you still have to wait for it to complete, but, you know, it completes fairly swiftly. And then we have what I would call transactional systems, which fundamentally people are, in one way or another, recording information in transactional systems. We have truly interactive systems, which are, you know, like graphical systems where when you move the mouse, the pointer moves, and you don't detect any difference in time. There is some latency, but it's so small you don't notice. It's way below 1/10 of a second. And we have real time, which is too fast for human beings, and that's computer-to-computer stuff. Now, the important point to notice here is that, you know, I've represented this in white arrows, but there is application migration that occurs. In other words, the same application moves from slow batch to medium batch to fast batch to a transactional basis to interactive and eventually to real time. And that happens all the time, but if you actually try and think of anything that has the word batch attached to it nowadays, or, you know, not a fast response time, it's nearly all in BI. I mean, there are other things, obviously, in rendering cartoons and stuff like that, where you have really big workloads, but, you know, in general, in the business terms, that's all BI. And that's what, in my opinion, in memory is going to disrupt this. In other words, it's going to change it, but it's going to change it rather fast and rather dramatically. And this is, first of all, the idea that the memory becomes a prime data storage medium, and that means, and we will ask some questions in the Q&A session about the meaning of this, but when memory becomes a prime data storage medium, then it's got to be able to do everything that disk currently does in order to do resilience, data management, the whole lot, you know. But if you look at this diagram that I've drawn, this slow data path at the bottom is characterized by data goes, you know, into an application onto disk, from a disk into maybe an ETL program back onto disk, from a disk into maybe a data warehouse program back onto disk, from the disk, from the data warehouse program to a data mart back onto the disk. In other words, this is a slow data path, and that data path with some operations can be hours, can even be days. Depends on what you're doing. Depends on how many steps there are. But every time you stop doing one step, the data goes back onto disk. And right at the top of this diagram, I'm talking about slow feedback. All the BI apps are actually going through human beings right now. At least nearly all of them are going through human beings right now. So a human being discovers something in some way or is notified of something in some way or other, and they feed back into the operational activity of the organization. And this is what I call actionable intelligence. It's like the reason we have the BI apps is so that in one way or another we can find things out about what's going on, whether that's a kind of analytic thing or it's driven by a dashboard. It's still the same thing. It's all about actionable intelligence. And the efficacy of the applications involved depend upon you actually being able to action it. It's no use discovering that the office is on fire without also being able to put it out in some way or other. So that, the path along the bottom and the path along the top is the way we operate now. But when you actually go into in-memory, it will be a fast data path from operational systems to BI applications, because they will probably even be using the same data. Or certainly they'll be using data that is as fast to get at as the other, because you have that capacity once you've got an awful lot of processors sitting over an awful lot of memory. You don't need to go to disk anymore, and therefore, obviously, disk might become a staging point where you're pushing things into memory, or alternatively, it becomes a backup device for, to cover the situation where, in one way or another, there's a failure that cannot be recovered by the memory itself. And that leads you towards the thing I've depicted in the center, which is a fast data path to BI, but also fast feedback straight into the operational systems without necessarily, of course, sometimes you're going to have to go through human beings, without necessarily going through human beings. And that's what I think we move towards. And what's neat about it, or what I think is neat about it, next slide, is that that's what the architecture looks like. It's not that complicated. It's like you have CPUs sitting over RAMs. Admittedly, there's going to be an awful lot of activity going on in those CPUs because you're going to be managing the data as well as actually processing the data in various ways. You're going to be running transactional systems, but also you're going to be running query-based systems at the same time across the same grid. And you can scale this out laterally. That's the idea. So this ends up being a much shallower hierarchy. And that's going to change everything, in my opinion. That simplifies the situation. However, we will not get there in a single jump. Okay, I'm going to questions now. First of all, the question to GridGain is, well, how big are you right now? So the first question I have is, what's the biggest number of servers currently deployed by a GridGain customer? How much memory is that at the moment? So what has practically been proved here?
Well, we've been proved basically, I think, to we ran the test a couple of years ago. The independent company, ran the test on Amazon, and they scaled us to, if I'm not mistaken, to 2,048 nodes. And they were running a fairly computationally intensive Monte Carlo simulation on that topology. From the point of view of a data capacity, I think the biggest we have right now is, I cannot tell you for sure because customer data we don't have an access to, but I think it's a few terabytes is what actually we have. I think a couple of customers running on that scale right now.
Okay, and do you mind, because I know you sometimes have to keep confidentiality, do you mind telling me what those applications are actually doing?
Yes, I would not be able to name the names, but for example, one client we have in London, it's a very large financial organization, and essentially they're doing an option pricing engine, and with the GridGain, they'll be able to move from kind of a kind of service bureau business model where they get the portfolios, get essentially the baskets, and then next morning they price them out and send out through FTP service. What they do right now is they do it in real time. You can send them a basket and you get a response back right on Tradi's blotter for the customer company. That you can send them a portfolio or a basket or anything, and they can price these options in real time. And that basically requires.
You've gone from hours down to seconds, I'm guessing. Is that right?
You've gone from overnight and emails in the morning, like the rest of the business operates in the financials today. I mean, anybody from financials probably know what I'm talking about. In the morning, they get like 20 emails with all the different reports and everything else from a previous trading day and insights and what have you. This company allows basically to have on the trading blotter essentially a button where you can click and send it, and the option pricing will be recalculated right in the spot. Pretty big deal, and that's basically was, the GridGain was foundation with that, because not only could it keep all the data in memory, they could basically very effectively parallelize the processing of this fairly intensive mathematics behind the option pricing.
Okay. So, well, my assumption is that GridGain is being used primarily for what I would say new applications. In other words, someone's decided either to rebuild something completely or to do something new entirely. Is that what your experience is?
To a certain degree, but I don't think it has anything to do with GridGain specifically. It's essentially when people decide to really inject the performance into this, existing application, they more often than not ending up basically redeveloping it. Now, I'm not saying from scratch, but at least they take certain parts of the application and redevelop it, because GridGain is one piece of a puzzle. There are many others. They can sometimes should redevelop the UI, should redevelop the data backup story or data storage completely, move from from one medium to another, or redevelop the database to be more aligned with what they need to do. So GridGain is, we have to be careful that the systems like GridGain, they don't just magically turn any system overnight into the high performance systems. It is a set of tools that you can use to build those systems. We've seen production rollouts literally anywhere from a week to 6 to 9 months. We literally had a few cases where people were able to essentially introduce GridGain within a week if what they call problem is embeddedly parallel. Essentially, when the parallelism is can be easily introduced without touching too many points in the systems. GridGain is known in the marketplace to essentially it can be rolled out within days and put in production. It just works.
Wow. Okay.
But I would say usually, on average, our clients probably spend months, 2, 3, 4 months before they can actually develop the system and introduce GridGain and retest everything and and put stuff in production.
Yeah, I can understand that why that would be in a lot of circumstances. I mean, it's going to be case for case, but also if you can easily push something into this environment, if you have, let's say if you've already written something in such a way that it actually transfers quite easily and you don't have to do too much to it, I can imagine that, yeah, you can go live quickly. That's
yes. One of the strengths of GridGain as a product, and one of the reasons for our success at this point, is that we remove the stigma of distributed systems being overly complex, taking months, and taking team of PhDs to do something about it. GridGain was in real life used within days in production, and that was a big win for us and big win for our clients, because they just download it, they play out with it, they inject some code, and all of a sudden it works on 10, 20, 30 computers right away.
I was kind of surprised that you had a big data message at the beginning of the presentation. So, but I can understand in certain ways how big data applications would be possible, or how you could utilize GridGain with big data. But I'm kind of interested, is this a kind of common request where people really are processing, towards the hundreds of terabytes, and they're thinking of using GridGain to assist?
Well, it's a good question. It is kind of surprising, but we're getting these questions asked on a daily increasing rate, to be honest. And the reason is pretty simple. For the last couple of years, we've been solving the capacity problem. Essentially, if you ask any significant analyst from, they'll tell you that basically the calls go like this: well, I download the Hadoop, what do I do now? So everybody basically got caught up in a kind of this wave that everybody needs to store data. So the storing is solved, and we have plenty of technology to store data. And by now, everybody is asking the question: okay, what do we do now? Well, obviously, the reason you're storing data is that you need to essentially process it. And let me ask anybody on the call, how many businesses do you know that can tell you with a straight face that, you know what, for today, in the next 10 years or 5 years, let's say, I'm totally okay with overnight processing? There are some, but not too many. Most of the business would say, you know what, even today we're okay with overnight processing batch orientation. In 2 or 3 years, we most likely have to have it fairly, in a real-time context, few seconds, so we can put it online, we can put somewhere else. And that's where people started realizing, hold on a second, we cannot afford to have a disk-only systems because that will never scale. Not because engineers are not smart enough, it just theoretically cannot scale for that type of SLA. So people start looking, okay, we're going to keep our data in a Hadoop or something like Hadoop or Greenplum or any other systems like that, but those are disk-based systems. And we can move our working set, which is a lot smaller. Even if you keep hundreds of terabytes of data, you never process the entire 100 terabytes in a single time, very rarely. Most of the businesses, 99% of the businesses, process less than terabyte as a working set at any given point of time. And if you can keep this terabyte, quote unquote, in memory, or 2 or 3 or 5 or 10, and keep it intelligently, then you have the best of the worlds. You can keep your overall data warehouse in the disk-based systems, and that you must do it because disk is the only way to do it, long-term reliably. But you can keep your working set in memory and essentially have a sub-second response on any type of BI analytics on that working set. And that's basically what lots of businesses they are realizing. Because, look, in almost any direction you point out, any small startups like Foursquare, everybody has an iPhone and Android device. This cannot be built with anything but in-memory technology. Any hyperlocal advertisement, any ad serving, look at any advertisement application. None of them can afford any delays whatsoever. And that permutates into the actual more traditional enterprise businesses with trading, with financials, with insurance, banking, everybody else. So it's kind of a long-winded answer to a question, but yes, we're starting to hear and starting to basically ask almost on a daily basis this question. How do you guys can help us to bridge this gap? We have lots of data. We're not okay with the overnight type of processing anymore.
Yeah, I can see it. Okay, I mean, if I didn't ask this question, the audience certainly was going to. This is just about in-memory. It's like the question really is a very broad question in the sense that, we have an awful lot of data management capability built into all of the database products that do various things for you, from security through to complete fault tolerance, failover, and so on and so forth. So the question is really, does the GridGain platform support all of that? If I wanted to just take a fairly sophisticated database application, remove the database and use only disks for backing up the data and stick it all in memory, can I do that and still get the same kind of support in all of those dimensions?
Well, it's a good question. I think if you ask me whether you can get exactly the same set of functionality and safety nets, probably my answer would be no. But it's a question, about how quickly you can approach. How close you can approach this. GridGain probably is one of the few products in the market today that gets you as close as possible, if not the closest, depending which particular vendor database you're going to compare us with. For example, well, quite obviously, GridGain supports full fault tolerance. You never lose the data. But probably most importantly, unlike many are, for example, NoSQL providers that support eventually consistent transactions. So essentially, they trade up a consistency of a data that you as a user now has to resolve, meaning essentially no transactions as we know them. They trade up this into the performance of writes into the cache. With GridGain, we support full two-phase commit transactions. So you're absolutely safe. Remember, like on my slide, I said we're giving you in-memory performance and database reliability. That was all about it. We're giving you a full transactions, so you can transact your memory. You can enlist it, for example, database transactions into the same transaction. And if your database fails, for example, we're gonna roll back the memory location as well. So you're never gonna get any inconsistency between the data in memory and the data in your storage if you have it. So that gives you a tremendous peace of mind because what I usually say to my customers is with GridGain, you can move money. You can move accounts. You should never worry about having no transaction in your system because GridGain is a fully transactional system. You can move money. You can do anything you can do in database. Now, if you ask me about every other particular feature that, for example, Oracle or DBMS would have versus us, I would say probably not. We're probably not going to have every other feature. In the same time, we have plenty of other features that Oracle would not have as well. So it's not a zero-sum game. We're going to win. We're going to lose somewhere, but so are other vendors as well.
Okay, Eric, I think I'm going to have to hand it back to you because I think I've run out of time. But if you want to use any of the questions I've got remaining, do so. But let's have the audience have at it.
Yeah, and we have some absolutely awesome questions from the audience here. So, Nikita, I'm going to start throwing these at you. We'll just go in order that they were submitted. So, one of the attendees asked, it's a very compelling question, does in-memory therefore render the relational model of data obsolete? If so, what is that replaced with?
Excellent question. The short answer is no, it's not rendering obsolete. DataGate provides the object store. So whatever you store in memory is a normal Java object or JVM objects, whatever language you use, Groovy, Scala, or Java, for example, that's going to be the object in that language. As I mentioned to you, most of our installations where GridGain is used always have a disk-based backend store. Almost always, whether it's a SQL database, whether it's HDFS, sometimes it's just a file system that people actually store. Because again, memory is volatile, and the disk is a lot more reliable as a long-term slow storage. So that, in my opinion, and I would say basically that I would say probably 60, maybe even up to 70% of our users are using SQL backing for GridGain. So that basically means that you still have that relational mapping between an object store and a relation mapping in a SQL database. If you just have HDFS, for example, from Hadoop, that problem, practically eliminated. But then you have a different story because you basically can store only byte streams in HDFS. So you still end up basically marshalling and demarshalling your objects from the object representation of a particular language to a byte stream that's supported by HDFS.
Okay, good. And we have a whole bunch of great questions here. Are you familiar with Twitter Storm? One of the attendees wants to know, how do you compare GridGain with Twitter Storm for real-time analytics?
Absolutely, yeah. Twitter Storm is an excellent project. It's a fairly new. I think Black Type developed, but Twitter acquired and decided to basically not to do anything with it, just open source it. The Storm is good for essentially streaming MapReduce processing. There is lots of deficiency in this approach only because it's very awkward to actually have a dynamically adaptive topologies. Topologies are pretty hardcore built. Another deficiency, in my opinion, it doesn't have a data story. It's essentially just a workflow, distributed workflow engine, pretty much like SunGrid was, in the last decade. So you have to use Cassandra or something like that or other projects to basically provide data store because very few computations in the real world are stateless. Even in Monte Carlo, and as stateless as it sounds, in real life, Monte Carlo is not a stateless computation. It has to have a state in it. So GridGain really provides you the state-of-the-art in-memory data platform. We provide you both computation, and obviously we provide you a much larger superset of functionality than the Storm, but we also provide you the entire data grid that can actually store data in a very effective, in a very intelligent way in memory. So I would say it's not really a valid comparison because you can probably compare a Storm with a subset of the compute grid functionality that we provide you, and that could be a judgment call. We obviously, overlap on that particular piece, but GridGain naturally provides you a lot more than that, at least at this point.
Okay, good. And if you would, just kind of go into this a little bit in more detail for people who don't know what you mean when you talk about stateless. Can you define what you mean by that and how it's important in this discussion?
Yes, the stateless computation essentially means that you can just pass a code around, and this code doesn't need any data. Let's imagine you compute the pi number. You don't need any data for the pi number because essentially pi number is a pure mathematics, it's a pure function. You can parallelize it. on many computers and compute pi number or e number in mathematics very quickly. But how often do you compute pi numbers in business? Very infrequently. I hope so. So the real computations in business, Monte Carlo is a very good example because in the pure mathematics, Monte Carlo is a very stateless operation. You throw your dice and you just compute this. In real life, actually, when you do the Monte Carlo, for example, for option pricing, for any kind of pricing, it is a very stateful operation. You have to have your portfolio data. You have to have some intermediate results stored somewhere. And even that primitive operation, as primitive as it gets, Monte Carlo, requires a certain state. And if you have any other, processing, most of the time you are going to have lots of data. It's your customer data, your web logs, your previous trade for the months, your previous geolocations. All of this is data, and most of your computations have to touch this data. That's why I don't want to say anything negative about Storm, but Storm is just solving one side of a problem, and they require you as a user, basically say, you know what, I'm going to take Storm for the basically streaming MapReduce, and then use Cassandra or MongoDB for my data store problem, and that introduces basically two products when you don't have to have them.
Gotcha. No, that's a very, very good answer. Thank you for going into detail. We have a whole bunch of questions here, so I'm just going to start firing them off in rapid fashion here. So what about any performance analysis tools available for distributed applications running on GridGain? And can you talk about some common pitfalls you've seen while developing such apps?
Yes, and when somebody asks me about benchmarks, I say the same story. I can build a benchmark that will beat anybody. And that's a very true statement in distributed systems. Literally, give me 2 days, I'll beat anybody. Because and that tells you how much the benchmarks useful in this business. Now, what we did find across many of our customers is that probably the best way. I mean, there's some obvious tips that we give to our customers, and most good engineers would actually know that you don't start more than you don't start 5,000 threads on a single JVM, things like that. But beyond just the obvious mistakes, probably the best way to test the systems and measure benchmarking the systems is to actually test it. We found that so often that even for ourselves, when we think we have a pretty good understanding, pretty good insight how the system would behave, and then we run actual payloads on it, and it behaves very, very differently. And that goes to how many CPUs is better to have, how many cores to better have, how big of a heap size on a single JVM should be, whether you're going to use the big memory support for off heap size allocation, only on heap. All of those different technical questions about the JVM processing we all know them. We think we know how they're going to affect the system. Believe me, in our experience, you can be 50% of the time you can be wrong. So the best way, take the real payloads and test it for your system. And that will give you a pretty good answer.
Okay, good. And one of the attendees has a couple specific questions. One asking, please discuss the Java program model using Hadoop to dynamically scale processes using GridGain.
Using Hadoop?
Yes.
We don't really, yeah, well, we don't really support Hadoop APIs because we're not a Hadoop project. I happen to believe we have a much better APIs, and I always keep saying that Hadoop is a great project for when it comes to HDFS. It's probably I wouldn't say great, I would say excellent technology. It's the best that happened in a long time when it comes to data storage and distributed file systems. When it comes to MapReduce, I probably have a biased opinion. I don't really like the MapReduce implementation in Hadoop. It's awkward, it's clunky, and it's really hard to use. I always keep saying that for GridGain we have our MapReduce example right in the back of our business card, and that's it. It's 10 lines of code. You can copy and paste it in your favorite IDE and run it. And I would challenge anybody in the market to produce exactly the same thing, and that's a running code. There's 10 lines of code in the business card. We'll run on 1 node, on 100 nodes, and on thousands of nodes, exactly the same way, just faster. So it's probably a much bigger discussion than we have time left. But I'll challenge you. I really welcome you guys to download GridGain and take a look at examples. It's probably the best way. If in engineering, you can quickly see the difference between our approach and somebody else's approach as well.
Okay, good. And what about applications for business activity monitoring, BAM?
Well, we in the Java world essentially we have a GMX connectivity, and as long as any kind of BAM or any kind of monitoring management networks and operations have GMX compatibility, we support that. But we also supply our own DevOps console that is extremely advanced. You can monitor the entire system, entire GridGain installation. You can monitor specifically data grid, compute grids. You can actually use SQL query to see what data inside of your memory. It's a very advanced. I think we're the only vendor in the market today that allows you to do that, to actually just write SQL like you would do against any database and see what's inside your memory in distributed fashion. So, and you can do a lot of different things. You can start and stop nodes. You can take remote thread dumps. You can analyze it. There's plenty of support that. So if that's not enough, then as I mentioned to you, we provide GMX connectivity. You can plug into practically anything in this ecosystem that supports GMX.
In terms of database accessibility, obviously JDBC, but do you do ODBC and SQL, or is that what you're talking about now?
Currently, we have, as far as the data store and cache store, we support JDBC, obviously anything in JDBC related. We support HBase, we support Hadoop HDFS directly.
Okay, gotcha. All right, one of the attendees has a pretty specific question, noting the data grid edition is shown as having two instances, compute grid and data grid, on different arrays of servers. Is that the case, or do they live together on the same servers, and how does that SQL functionality work, and to what degree?
No, obviously, the data grid and compute grid lives on the same node, the same JVM. As a matter of fact, GridGain has a very peer-to-peer architecture. There is no servers, there is no clients. Every node can act as data grid, compute grid node, or both. Most of the time, I would say 99% of the time, they act in our systems as both compute and data node. When it comes to SQL, it's very simple. We have our own implementation. You can essentially just issue the query. Let's say select star from string or something like this, and if you store string objects in your cache, you get all the objects in your cache. And that's going to be, we're going to take care of all the distribution, all the collocation of data, all the aggregation of data, and you have a normal JDBC interface. So if you have a system that deals with JDBC, you can very safely replace it. I would say with few reservations, you can replace that with the GridGain in the backend and still use JDBC interface.
Okay, good. Here's a really good, very specific question. One of the attendees writes, can you talk more about how key value store pairs are enough to describe facts about objects? Semantic databases normally talk about triplets, object, attribute, value. So the question is, are key value pairs enough to describe everything you normally have in a database?
Well, we got to be careful here because we don't store key value pairs. We store objects in database where the key and a value can be in any arbitrary object in Java. So the object can be triplet itself. And we actually have few users that use GridGain to implement semantic webs or semantic web applications that are basically based on triples. And as far as I remember, they just basically use keys as the keys and the value as a triple. And that works perfectly fine. So some of the queries and some of the inference engines you can build on semantic web applications, those may require an additional coding because we don't support inference engine out of the box. But I don't see from a data format or from a data representation, I don't see any problem here. And because I do know we have a number of customers who do semantic webs with GridGain.
Okay, and here's a question, just kind of a basic one. Are there any other software vendors out there that are using your technology? In other words, the specific question, any vendors offering products, services, or functionality delivered by or on top of GridGain?
Yes, we have the whole OEM program, as a matter of fact. We have a number of paying customers that use exactly in OEM fashion. Unfortunately, I cannot name the names because part of the OEM is essentially it's OEM contract that they use GridGain inside. But yes, GridGain is actually a very interesting technology in the sense because not only we have all the legal rights to issue the OEM license, which is a fairly rare position in open source, but we also have the architecture of a system based on very kind of pluggable core. You can think about GridGain like a Lego block, so you can plug and play anything you want to have, and that is extremely attractive to OEM vendors because they can change a lot inside of GridGain without redeveloping the product.
Okay, here's a really good question. So is GridGain sort of a MapReduce for in-memory and compute, or more of a NoSQL alternative, or a hybrid of both?
Oh boy, we can spend probably another hour on this question. I don't want to get in a pitfall with the NoSQL comparison because that's a fairly loaded question. There's a lot of overlap between if you take if you take Couch, if you take MongoDB, if you take Cassandra, take GridGain, and there's plenty of overlap. Obviously, we're not solving just black and white problems independently, exclusively. I think the biggest differentiator for GridGain is two things. We're the only vendor today that combines both a state-of-the-art compute MapReduce platform with a data store. And we're not talking about some toys like MongoDB has or anybody else. We're talking about a full-fledged HPC platform for Java. And I take it, and I'm saying it very seriously. And second of all, and that's probably the biggest difference between NoSQL storage, is that we support fully transactional behavior rather than eventual consistent transactions. There are use cases for both. I'm not saying either one is bad or good, but that's the difference. Most of the NoSQL product based on eventual consistency, where data is inconsistent, but it's traded up for right performance. With GridGain, you get the same transactional behavior as you get in database, and we're trying very hard to maintain the performance on the similar levels like NoSQL databases, because obviously it takes more round trips, it takes more network trips to support two-phase commit transactions, and therefore naturally these systems tend to be a little bit slow on the writes, but a lot quicker on reads. We took a lot of optimization, it took a lot of algorithm approaches to really improve our write performance as well. So those are going to be the two major, I wouldn't say difference, but those are going to be two major qualifiers when you talk about GridGain and some other vendors that actually are pretty good in their own niche.
Okay, and we still have a bunch more questions, but we really try to keep these at 75 minutes or less. So let me just throw a couple more at you, and we'll wrap up. Here's a basic question. I just was on a big SAP webcast today in which they're talking about their whole new vision, and obviously HANA is a big part of that. And obviously I don't really want you to comment too much on what HANA does, but how would you compare what you're doing with SAP HANA?
Again, somewhat similar. I don't think HANA has a strong story in the computational side. Again, that's a usual Achilles heel. Almost anybody treats computation as a second kind of citizen, except Storm. Storm treats it as first, but it lacks, the data side as well. And, I do believe that HANA will always be a link to the SAP ecosystem. So if you're in a SAP customer with R3 or anything you have, HANA will always, in my opinion, at least for now, that's what I know about it, will always be essentially be that plugin to the SAP ecosystem that gives you this in-memory performance. I don't think it's going to be, a strong independent product. That's my current reading of HANA, and there's a very little information technology-wise. So what it is, but it's a memory system. So at least on that level, we're pretty similar. I think approaches are quite a bit different.
Okay, good. And here's an interesting question. One of the attendees wants to know, how do you deal with what he's calling it split brain issues, where the compute is actually is split into two servers, I guess?
Yes, excellent question. It means we have a pretty strong crowd on the webcast. I can tell with a straight face we have a best in the industry support for split brain problems, because not only we detected, we're giving you a pluggable segmentation policy handling. It's a bit technical probably for most of you guys, but not only we detected, we're giving you capability to react to it and plug in your own detection mechanisms to it. Nobody in the industry does it, because we recognize it's a very big problem in production systems. Not only we detect that you can plug in your own, for example, you can pick certain network device, you can pick any server database, and we give you different policies. How do you react on this network segmentation? It's a very big deal problem. because you can get segmentation, and that can lead directly to data inconsistency in production systems. So the more knobs, the more things you can configure and plug in into data segmentation, it's the better. And we undoubtedly have one of the best support in the industry for that.
Okay, well, boy, we just threw a whole bunch of good questions at you. Thank you so much to everybody out there for all of your great questions. You really help us make these events just as good as they can be. And honestly, I couldn't come up with some of these questions, so thank you so much for sending those in. Folks, this does conclude our webcast. You can see July's Disruption Month. We're going to have Big Blue in the briefing room next week. That's right, IBM is stepping into the briefing room. And we'll take a week off most likely as I go to the TDWI conference in San Diego. So if anyone's out there, look for us there. And, of course, August is Analytics. It's a sold-out month. Keep your eyes peeled for what's coming down the pike. Folks, with this, we will conclude our event. Speakers, if you would stick around for a quick post-event discussion. And with that, folks, we will say take care. We'll talk to you next time. Bye-bye.